Welcome to Engineering Studio with Dr. Mohammad Tahir. In this video, we are going to discuss about the general procedure for structural design as well as the methods available for design of structures. So first of all, what is structural design? Structural design is the systematic investigation of strength, rigidity, and stability of structure. So when we are going to design a structure, we investigate these three things: strength, rigidity, and stability. Whether the structure is capable to resist the applied load, and we also check whether our structure is rigid enough to limit the deflections within the allowable limit. We also check the stability, whether this structure is stable under the application of load. Next is objective of design. The objective of design is to produce a structure which is capable of resisting all the applied loads without failure. So it should resist all the applied load without failure. And the failure can be of three types. Either it is a strength failure, rigidity failure, or stability failure. So here we have a strength failure. Under the application of load, the material is failed. So it is termed as strength failure. So our structure should be capable to resist all the applied load without strength failure. The second is rigidity failure. The rigidity failure is our structure should have deflections within the allowable limits. If a structure have excessive deflection, so we will consider it as a failure. The third is stability failure. Under the application of load, structure should not collapse, it should not overturn. For example, in this figure we can see we have a truss, but when we apply the load, it will collapse, it will turn it like that. So it is an unstable structure. To make it stable, we need to add this member. Similarly, here if we have all the connections, pin connections for this frame, and under the application of horizontal load, this structure will collapse. There will be no material failure, but it will be a stability failure. Structure will be unstable. So we need to make sure that our structure should not have these three types of failures. Okay, next is design procedure. So design procedure, generally it consists of 4 steps. The first step is to establish the load and design condition. The second step is analysis based on the applied loads and design condition. And the third is proportioning and selection of material. So this is basically our design. The previous two are related to analysis. And finally, we need to communicate our design selections. So these are the 4 steps which are required for the design of any structure. Either it is concrete structure, steel structure, wood structure, composite structure, whatsoever is the type of structure, we will follow these 4 steps. So first of all, establishment of load, establishment of design condition. So we need to decide the function of the structure, general layout and dimensions. These two will come from the architectural drawing. Then structural system, we also need to decide whether it will be a frame structure, shell structure. So this is before the design. So we need to make the decision about the type of structural system. Then temperature and environmental conditions. So we need to consider the variation in temperature as well as the environmental condition, because the temperature variation will affect the stresses or the loads. So environmental condition will help to decide about the construction material, whether it should be a concrete, steel, composite. If, for example, the environment has air as well as moisture, in that case we will avoid steel structures. For example, in case of marine structure, we will avoid steel. So the next step is establish the load. So based on our function, as well as the environment condition and the location of the building, we need to decide the dead load, live load, wind and earthquake load. So these loads must be supported by the structure. The next step is analysis. So analyze and compute internal gross forces, which include thrust, shear, bending moment, twisting, as well as stresses, strain, deflection, and reaction. So based on the applied load, or due to the applied load, we need to calculate the internal gross forces, as well as the internal gross forces because of temperature, changes in temperature, shrinkage, creep, and other design conditions. So we need to calculate the internal gross forces as well as the internal stress, strain, and deflection produced because of applied loads, changes in temperature, shrinkage and creep, and other design conditions. So next is types of analysis. So while designing a structure, we need different type of analysis. So mainly we encounter three type of analysis for the design of structure. The first one is static analysis. In case of static analysis, we determine the internal forces like shear force and bending moments. So to perform the static analysis, we need loading conditions and the boundary condition. We need the loads as well as the boundary conditions. We don't need any material or section properties. For example, while analyzing a beam, simply supported beam, we just consider that we draw a line diagram and apply the load that it is a beam subjected to uniformly distributed load, and we calculate shear force and bending moment diagram like this. And for this calculation, we do not require any cross-sectional as well as material properties. So this is termed as static analysis. The second type of analysis that we may perform is stress analysis. For stress, so this stress analysis is performed for stresses and strain. So if we want to calculate the stress and strain inside a section or inside a structural member, so then we perform stress analysis. So it is based on the material strength, section properties, and loading conditions. For example, if we have a column and it is subjected to a point load at the top, axial compressive in downward direction, and we know its dimension B and D. So in that case, we require to calculate the stress. Under the application of load P, what will be the stress in that column? So we will calculate the stress sigma is equal to P over A, or P divided by B times D. So this type of analysis is termed as stress analysis. So we have calculated the stress under the application of load, or due to the application of load. The third type of analysis is capacity analysis. So if we want to calculate the resistance or capacity of a member, then we use capacity analysis. So in that case, we need material strength as well as the section properties and loading conditions. So based on these information, we calculate how much resistance this section will provide or how much will be the capacity of that section. For example, if we have a column again, and we know its B and D, mean its area, and we also know that it is a steel structure with Fy 420 megapascal. So now we have the material property as well as sectional properties. Now we need to calculate how much load it will bear. For example, this B as well as D is 10 millimeter and 10 millimeter. So P will be equal to sigma into area, or stress into area. So stress here is 420 and area is 10 by 10. So 420, or we can say 42 kilonewtons. So this member will resist 42 kilonewton load. So this is the capacity analysis. Based on the sectional properties as well as the material strength, we have calculated its maximum resistance. So while designing, we need to perform these three types of analysis most of the time. The next is proportioning and selection of materials. So it consists of proportioning of section and selection of material for the members and connections. So sometimes we decide the material at the initial stage during the design conditions, that what will be the material for the structure and how much will be its strength. For example, we have decided that it will be a steel structure with the yield strength 420 megapascal, for example. So then we only need to proportion the structure. What will be the cross-sectional dimension and the shape of the cross-section. So our selected section should be capable of resisting all the applied loads. So there are two design approaches which are mainly used. The first approach is termed as direct approach and the second is indirect approach. So in direct approach, we calculate internal forces from the load, we perform the static analysis, and then compare with the material strength for proportioning. So from load, calculate the internal forces and then compare with the material strength for proportioning. For example, we have a beam. For example, it is a steel beam with rectangular cross section and it is subjected to uniformly distributed load. For example, it is 10 kilonewton per meter and the length of the beam is 1 meter. So under the application of this load, the bending moment will be WL square by 8, so which is 10 into 1 square divided by 8. So it is 10 divided by 8. Or we can say 1.25 kilonewton meter. So now we have calculated the internal forces based on the applied load. The next step will be proportioning of the sections. What will be the section of this beam? What will be its width and what will be its depth? For example, we have decided that it should be a square section. So in that case, to resist this bending moment, we know that the stress should be equal to my over I. So the stress produced because of this bending moment is my over I. And we know that our material is a steel structure with Fy 420 megapascal. So it means the maximum stress that can be produced in the section is 420 megapascal. So we will compare this stress with the material strength. So 420 is equal to M is 1.25 and Y is, for example, here B and D. So it is D by 2 and I is D into D cube over 12. As we know that, as we have decided that width and depth both are equal, so I write here D. So from here, when we will solve this equation, so we will get the value of D. How much will be the D? So once we have D, so it means we have the cross-sectional dimension. We have proportioned our structural member. So this is the way of designing structure and it is termed as direct method. So from the applied loads and conditions, we have calculated the internal grass forces, and because of that internal grass forces, we will compare these internal grass forces with the material strength, and as a result we will get the sectional properties or proportioning of the section. The second approach for the design is indirect approach. So in this case, from the material strength and assumed section properties, we will calculate the maximum load that can be sustained by the supposed or assumed section, and then we will compare it with the applied load. It means, first of all, we will select an arbitrary section, and we will also select the material properties, and we will perform the capacity analysis to calculate its strength or maximum capacity. Then we will compare that capacity with the applied loads. If the capacity is more than the applied load, it means our selected section is okay. Otherwise, we need to revise our section. So this is a trial procedure. For example, we have selected a section, a rectangular section of 10 by 10 millimeter, and Fy is 420 megapascal. And the applied load is, for example, P is 35 kilonewton. So we will check whether this section is, our assumed section is capable to resist this 35 kilonewton or not. So its capacity P is equal to As into Fy. So As is 10 by 10 and Fy is 420, so it will be 42 kilonewton. So the capacity is, nominal capacity is 42 kilonewton and the applied load is 35 kilonewton. So it is greater than Pu applied load. So it means okay, our section is okay. Once we have proportioned our sections, the next is to communicate. We have decided the dimensions of the section, we have decided the material. So next is to communicate for the execution purposes. So the communication of the design outputs is made by using journal notes as well as drawings. So we will make the drawings, we will write some journal notes, and we will draw the sections, elevations, and different details of connection in the drawing sheet. So based on these drawing sheets, the contractor will be able to execute or construct the structures. Next is basic design equation. So the basic design equation is the capacity or the strength of the member should be more than the applied load, or we can say the required strength multiplied by the factor of safety. So this is actually applied load Pu multiplied by factor of safety. It should be less than available strength Pn, the nominal strength. For example, if the applied load is 100 kilonewton and the capacity of the section is 120 kilonewton, so it means our structure is safe. But if the available capacity is less than 100, it means our structure is unsafe. So we need to fulfill this criteria for the design. So there are two different methods available for the design of steel structures, mainly ASD as well as LRFD. ASD means allowable stress design method, and LRFD, it is load resistance factor design. So in case of ASD, we consider the service loads. We do not increase the loads, we just combine the load there and consider their maximum intensity based on the probability of occurrence. And the service load should be less than the nominal strength divided by factor of safety. And in case of ASD, we apply the factor of safety on the strength of the member. For example, here in this figure we see here is the nominal strength of the member of the section. we apply factor of safety and reduce this strength and bring that strength into the elastic range. And then we compare it with the service loads. So the service load should be less than the available capacity, allowable capacity. So this is the approach which is used in case of allowable stress design method, and we term this stress, reduced stress, as allowable stress. In case of LRFD, we factored the service loads. We apply some factor of safety on the applied service loads and then compare it with the nominal strength. So here U times service loads, so we have increased the service load by multiplying it with the factor of safety, and we have also reduced the nominal strength by multiplying it with the strength reduction factor phi. So this term, phi times nominal strength, it is termed as design strength, and this is factor load. So the factor load should be less than the design strength. So in case of LRFD, we reduce the nominal strength by multiplying it with the phi factor. It is a very small factor. In case of steel or tension member, it is 0.9, sometimes it is 0.75. And we also increase this service load by multiplying it with the factor. And then we compare this nominal strength with the applied factor loads. And in that case, again, the nominal strength or the design strength should be more than the factor loads. So this is the approach which is used in case of LRFD. We apply the factor on load as well as on the resistance. So next is factor of safety. What is factor of safety? So factor of safety is required to bring structure from state of collapse to usable state. For example, if we design a structure like that, the PU applied load is equal to Pn, the nominal capacity. In that case, if somehow the applied load increases the PU value, so in that case our structure will collapse. So there may be some uncertainty in the applied load. So if in any case the load increases the nominal strength, then the structure will collapse. Or otherwise, if the nominal strength is less, there is some uncertainty or there is some flaw during the construction, and the strength of the section is less than as expected. So in that case, again, if the load reaches up to PU, the structure will collapse. So to counter that, we need to apply some factor of safety. Either increase this PU, this P, by multiplying it with the factor of safety, or reduce this Pn by dividing it with the factor of safety. So both approaches. This is LRFD approach and this is ASD approach. So these factor of safety are actually applied to bring our structure to usable state from the state of collapse or unstable state. Other than this, it also covers for the other factors like uncertainties in applied load. For example, if we have designed a classroom for 200 people, but there is a possibility that more students or more people can gather in that classroom. For example, 300, 400 students can gather in that classroom. So if we have not applied the factor of safety, our structure will collapse. So the deflection should be small at service loads. So we also apply the factor of safety to keep our deflections within the allowable limits at service loads. It also covers the uncertainty in material strength. So material strength can vary inside the member as well as if we have fabricated the different structural member in the factory, so their strength may vary a little bit. For example, if we test 3 rods under tension, their strength will be somewhat different. For example, its strength is 420, its strength is 415, and its strength is 425. So there is small variation in strength. So mostly we use the average value. So we will report its strength 420. But if the strength is 415, what will happen? So the structure will fail at the service loads. So to counter this, we need to apply the factor of safety. So instead of this average, we reduce it by, for example, 0.9 to bring it to some lower value. So it also covers in part poor workmanship. So during erection of the structure, for example, in case of column, we have this condition that there is no bending moment acting on this section. But if during construction it is not perfectly vertical, it is somewhat inclined. So in that case, due to eccentricity of load, this eccentricity, a bending moment will generate in that section. So to account for that unforeseen circumstances, we need to add some factor of safety. So it also covers unexpected behavior in case the theory is not fully developed. Most of the time, or sometime, we can say, the theory for the design is not 100% developed. So if we do not apply the factor of safety and the behavior is different as expected, so in that case the collapse can occur. Most of the time we make some assumptions for the development of design equation. So to account for the actual condition, we need to apply some factor of safety. It also covers the natural disaster. Although we consider the dead load, earthquake load and wind loads while designing the structure, but there is possibility that magnitude of earthquake is higher than the expected. So in that case, our structure will collapse. To account for that, we need to apply some factor of safety, that if in case a higher magnitude earthquake hit the structure, it should not collapse. To cover residual stresses produced during fabrication. So during fabrication, during welding, erection, bolting, so some residual stresses can produce in the structure. So we need to account for that. So for that, we reduce the material strength and we increase the applied loads by multiplying or by applying the factor of safety. The next is load combination. So it is almost impossible that all loads occur together with their maximum intensity. There is possibility that all the loads do not come at the same time. So a load combination combines the different type of loads depending on the probability of occurrence and their expected intensity. That which type of load will occur simultaneously, and we combine these loads based on their probability of occurrence, that at one time which type of load can occur simultaneously. So in LRFD design, the load combination are considered along with the factor of safety. So in case of ASD, we combine the load without adding the factor of safety, but in case of LRFD, we combine the load as well as we factor them. For example, here we have combined the load, dead load and flood load, but we have also multiplied it with factor of safety. Here dead load and live load, and it is multiplied with the factor of safety. And this factor of safety is again based on the expected intensity. Next is design specification. So the adequacy of structural member is determined by the set of design rules. So these design rules are called specifications. So these specification includes design formulas that guide the designer to check the strength, stiffness, proportion and other criteria that may govern the acceptability of the member. For example, in design specification there is a limitation of 20 millimeter maximum deflection for a beam. For example, I am just assuming that. So if your design structure has a maximum deflection within this limit, then it will be accepted, otherwise it will not be accepted. So there are a variety of specifications that have been developed for both materials as well as for structures. So each is based on year of research and experience. So some of the specifications for related to steel structures are given here. For example, AISC, American Institute of Steel Construction, AISI, American Iron and Steel Institute, AWS, American Welding Society. ASTM, American Society for Testing and Materials. So if you construct a structure or if you design a structure based on the available design specifications, then no one will be able to question your design. In case if a structure fails, so the investigation will start and they will check whether your design is as per design specifications or not. If your design is as per specifications, then you will not be questioned. So next is revision of basic concept. This will be covered in the next video.